Everything around you is made out of atoms of different elements, but it's pretty rare that you encounter pure elements in your everyday life. No, these elements combine to form chemical compounds that make up our physical world. The bread of that sandwich you're eating, the air you breathe, the heart beating in your chest, and the blood moving through your veins, all made of chemical compounds rather than single elements. But of course, for elements to come together and create a compound, they need to form a chemical bond. And perhaps unsurprisingly, chemical bonds come in different flavors, for lack of a better term. Not every bond is the same, so let's take a look at how those bonds literally shape our world. Hello and welcome to the Chemist's Codex. My name is Peter and I like to find stories in whatever catches my interest because I believe those stories can teach us more about ourselves. Chemical compounds make up everything we see, touch, taste, and smell. The only basic sense we have that doesn't directly interact with chemicals is hearing. Sadly, it is not currently possible to hear a chemical. But as chemicals make up, well, everything, it's important to understand how elements combine to create chemical compounds, because a chemical bond is not as simple as you might think. For starters, there are multiple types of chemical bonds, which can arise due to which specific elements are bonding with each other, and that's something I want to shine some light on, and hopefully by the end of this video you'll have a better appreciation for the chemicals that make up our world. But before I dive into chemical bonding, make sure you subscribe and hit that notification bell so you don't miss any of my upcoming videos. And now that you've done that, on with the science. As you go about your day, what kinds of things do you do? Maybe you go for a jog, maybe sit down to read a book, perhaps you decide to take a midday nap. No matter what it is you decide to do, you'll almost certainly eat something at some point, and you will definitely be breathing while you do so. The food you eat is to give your body energy. Carbs, protein, fat, all of it is meant to give your body energy to get through the day. And one of the most basic processes by which your body does so is something known as cellular respiration. At its most basic, this is the process by which your cells take glucose, sugar, and react it with oxygen to produce carbon dioxide and water. This reaction also releases energy stored within the sugar. It's essentially the reverse of the photosynthesis reaction that takes place in plants. But all four of those molecules I mentioned have something in common. They all utilize the same type of chemical bond, what we call a covalent bond. So how does this type of chemical bond work? Well, first we need to understand a couple things about electron behavior in an atom, because all chemical bonds will involve looking at electrons. First, there's the concept of valence electrons. These are the electrons furthest away from the atom's nucleus in the outermost orbital and are the ones directly used in chemical bonding. We can, broadly speaking, determine how many valence electrons an atom has available by looking at what column of the periodic table the element resides. Hydrogen and the elements below it have 1 valence electron. Carbon and the elements below it have 4 valence electrons. Oxygen and the elements below have 6 valence electrons. Then there's what's known as the octet rule. Again, broadly speaking, atoms want their valence orbitals to be full, and this usually corresponds to having 8 electrons in that orbital. So most chemical bonding will involve moving electrons between atoms to satisfy the octet rule. The name covalent bonding might make a bit more sense now. Covalent. It's the sharing of valence electrons. You can think of it like a game of tug of war. The two sides pulling a rope made of electrons taut between them. A single covalent bond is made up of 2 electrons, which are shared between 2 atoms. There are also double and triple bonds that can be made, each one using 2 more electrons. So we can look at carbon dioxide to examine this a bit more. The carbon atom makes a double bond to each of the oxygen atoms, so we end up with a molecule that looks something like this. What's actually happening when a covalent bond forms is that the valence orbitals of the atoms are overlapping with each other and combining, producing a larger orbital over the entire molecule. But with covalent bonds and covalent molecules, there are actually 2 types of covalency that exist. There's polar and nonpolar. To understand the difference between these, you first need to understand how atoms of different elements attract electrons. This is something we call electronegativity. In short, some atoms in a covalent bond are going to pull electrons towards them to a greater degree than other atoms. With the tug-of-war analogy, you can kind of think of electronegativity being how strong a side is. If one side is stronger than the other, the rope will be pulled a lot further to one side, but if the sides are roughly equal in strength, then the rope will stay largely in the middle. Elements in the top right of the periodic table tend to be very electronegative, so they'll very easily pull electrons away from other elements, oxygen being one of the most electronegative elements in existence. So if we look at something like water, we can see how electronegativity creates a polar molecule. Oxygen pulls electrons away from the hydrogen atoms, and then the oxygen atom also has 2 lone pairs of electrons. These are essentially electrons that don't participate in bonding. So there are extra electrons already there, and then the oxygen is pulling electrons away from the hydrogen atoms. That means that electrons are going to be really concentrated around the oxygen atom, and electrons have a negative charge. So in a molecule of water, there exists a small negative charge on the side with oxygen, and a small positive charge on the side with the hydrogens. This is why we call it a polar molecule. It has a negative and positive side, a north and a south pole, like a tiny little magnet. This is the example where the tug-of-war rope is pulled more to one side over the other. And then there are nonpolar molecules. These are ones where the electronegativity between atoms is largely balanced, and we can see this in play with molecular oxygen. Because the oxygen we breathe is in this form, O2, two oxygen atoms with a double bond between them. Now, even though oxygen is one of the most electronegative elements, this molecule is nonpolar, because the oxygen atoms are equal in strength. The tug-of-war rope isn't going to move all that much between them. The electrons are evenly distributed throughout the molecule. So that's covalent bonding. But let's keep moving. One of the most common substances humans use to season our food is salt. We put it on things both savory and sweet. We use it to preserve food to make it last longer, and it's one of the staple seasonings for practically every meal. And I'm assuming that most of you watching this know that table salt is sodium chloride. I specify table salt here because in chemistry, a salt is really just a metal combined with a nonmetal. But anyway, do you know what a molecule of sodium chloride looks like? You might think it's something like this, a sodium atom connected to a chlorine atom. But that's not quite correct, because salts use a different kind of bond. They employ what's called an ionic bond. Ionic bonds arise when the electronegativity difference between two atoms is so great that the more electronegative element rips away electrons completely from the weaker one. Going back to the tug-of-war analogy, this would be if one side was so strong that they yank the rope entirely away from the other side. This results in the creation of ions, atoms that have a charge to them, either positive or negative. And because opposites attract, the negative ion will be attracted to the positive ion, and they form a bond. Unlike covalent bonding, this doesn't involve overlap of orbitals. Instead, it relies entirely on the electrostatic attraction felt between the positive and negative ions. But then what does a molecule of sodium chloride look like then? Well, that's kind of a trick question. Sodium chloride, as well as other ionic compounds, doesn't form discrete molecules like water or carbon dioxide, at least not at normal conditions. Ionic compounds tend to exist as solids at ambient conditions, and they form a crystal lattice. The atoms of the compound create a pattern which can be repeated over and over to build up the crystal. Sodium chloride has a pretty simple one. In fact, it's so simple that its crystal structure is referred to as a rock-salt lattice. Start with a cube and put sodium atoms at the corners and in the middle of each face. Then put chlorine atoms in between all the sodium atoms, including in the middle of the cube. This is what's called a unit cell. It's the simplest unit of a repeating pattern. You can take this and repeat it out as many times as you want to build a crystal. And there are loads of different types of crystal structures. Some are cubic, others are hexagonal, and some are more rhombohedral. The type of unit cell has to do with the lengths of the sides, the angles between them, and then where the atoms are located. And while I've mainly been focusing on single atoms in a crystal structure, it is possible to have a crystal made up of discrete molecules, and the perfect example is already in your kitchen. Sugar is a single molecule, specifically sucrose, that is capable of creating a crystal lattice. Specifically, it creates what's called a monoclinic crystal structure, one of the types that is considered low symmetry. But going back to ionic compounds, while simple table salt is one of the more common examples you might be familiar with, ionic compounds are going to be all around you. If you look at the ingredients list of just about anything, you'll likely see a few. Sodium benzoate is common in sodas as a preservative. Sodium bicarbonate, also known as baking soda, is used as a leavening agent in baking. Phosphates are important for biological processes. Anytime you see something that has sodium or potassium, or something that ends with ate or ite, that's probably going to be an ionic compound. And now there's one final type of bonding I want to touch on. Among all the things in your house, you almost certainly have something made of metal. This could be the cutlery you use to eat your meals. If you have a razor, the blades are likely made out of stainless steel. You've probably used aluminum foil to store some leftovers in your fridge. Or the wires carrying electricity through your walls are made of copper. Metals have been an important material throughout human history. We've had the Bronze Age and the Iron Age, or when talking about media, we'll often talk about them in terms of a Golden Age and Silver Age and so on. Part of what makes metals so useful for us is their strength, but also how ductile they can be. Copper is ductile enough that it can be readily drawn into long, thin wires. Gold is so malleable that you can easily work it into different shapes with simple tools. And part of what makes metals so moldable and changeable is the type of chemical bonding they undergo, what we call metallic bonding. This works differently from ionic bonding, where electrons are ripped away from an atom, but it also works differently from covalent bonding, where electrons are discretely shared between two atoms. Instead, metallic bonding is kind of a combination of covalent and ionic. To start, metallic bonding, like covalent bonding, involves the overlap of orbitals, but what's different is the metal atoms are going to be surrounded by up to 8 other atoms. So the orbital overlap isn't just between 2 atoms, it's between pretty much every atom in the metal. You essentially have massive orbitals covering the entire material. What this means is that the valence electrons in the metal become delocalized. They are not bound to any specific atom. They can roam free around the entire metal lattice. This is what allows metals to conduct both heat and electricity very easily. The electrons are freely able to move around, allowing for easy transfer of energy. And then, like ionic compounds, metals create a crystal lattice. They typically arrange themselves in some form of cubic lattice, but there are several that also take on a hexagonal lattice. Of the cubic lattices, this is either body-centered cubic, atoms at the corners with another at the center, or face-centered cubic, atoms at the corners with more atoms at the center of each face. And this sea of electrons and regular lattice structure is what allows metals to be so ductile or malleable. The lattice allows the atoms to slide past each other while the sea of electrons keeps the atoms bound together. Some metals can also take on different types of crystal structures depending on various factors when the atoms are locked into place. Iron is a perfect example of this and is something blacksmiths are well aware of. Iron has several different crystal forms. There's ferrite, austenite, and martensite, among several others. You can convert between these crystal forms by heating up the metal to specific temperatures, adjusting the amount of carbon dissolved in the metal, and controlling how fast the metal cools down. So those are the 3 main types of chemical bonds. Covalent bonds will join nonmetals together, ionic bonds will bond metals to nonmetals, and metallic bonds link metals together. Covalent bonds are what you'll most likely encounter when dealing with organic materials. The food you eat will be made of covalently bonded atoms, your very DNA is comprised of covalently bonded molecules. Plastics are also going to be largely covalently bonded molecules, being made up of long chains of organic molecules. Ionic bonds might be a bit more rare in your everyday life, but they are by no means any less important. The sodium you get from salt is vital to many of your cellular processes, including helping you stay hydrated. When people talk about electrolytes, it's largely going to be sodium they're referring to. And then metallic bonds are going to be everywhere. Any sort of metal, from the fork in your hand to the change in your pocket, is reliant on a sea of delocalized electrons to hold the atoms together. And hopefully now you can have a better understanding and appreciation for the chemical bonds that make up not only the world around you, but also make up you. Thanks for watching. I'm not sure how well this video is going to do. I tried my best to make it interesting, but frankly I was struggling to find a solid video topic for this week and I needed something I could easily talk about without having to do too much research. But let me hear from you. Did you like the video? Is there anything I mentioned that surprised you? Or is there something you want to know more about? Leave a comment and let me know. And hey, since I could use some ideas for videos, go ahead and leave a comment if you have a specific topic you want me to make a video on. I would be grateful for whatever ideas you guys have. And if you want to see more videos about the chemistry that builds our world, make sure to subscribe and hit that notification bell so you don't miss my future videos.